A very good morning to all the participants. A very good morning to the chief guest, my dean. This is Vidya welcoming you all to the fourth day of this one week online short-term training program. Today we have with us our eminent speaker, Dr. Badri Toppur. He is the associate professor and head in Center of Excellence in Rajalakshmi School of Business, Chennai. We also have with us Dr. S. Manivanan, our dean and convener of this program, and Mr. Ganesh Babu, who is system administrator and technical in charge of this program. So may I call upon Dr. S. Manivanan, our dean, to welcome the gathering, please.
Am I audible, Vidya?
Yes. Yes, sir. Yes.
Good morning. Good morning, everyone. It gives me immense pleasure in seeing you back for the fourth day of our short-term training program on research methodology organized by Faculty of Humanities and Sciences, Dr. MDR Educational Research Institute. Really, I am proud to have such an eminent person like Dr. Badri Toppur for presenting a valuable session in our STTP. I know Dr. Badri sir for a longer period. I used to invite him for giving technical talk on various topics, especially SPSS, advanced mathematics, something like that, for our UGPT mathematics students in our university. He is such an eminent scholar. Sir is working as a associate professor in Rajalakshmi School of Business. Rajalakshmi School of Business is a premier institute in Chennai, doing wonderful job for the MBA department. Of course, another thing is Sir is working for the Center of Excellence also in that college. And I am really proud to have such an eminent person who has done his UG from St. Stephen's College in New Delhi and his PG from IIT Mumbai MSc Mathematics. IITN, former IITN, is back to our STTP. It's a great moment. Also, he has got second PG from Clemson University, South Carolina, USA, and of course PhD from University of Massachusetts. Such a great person we are having today. I wanted to, I am requesting all our beloved participants to listen to him and understand the basics, how we can equip ourselves with the help of this kind of mathematical basics. This kind of practice only will enable all the research scholars to come out like a eminent person like Dr. Badri. Of course, I wanted to praise Dr. Badri. After his graduation, he didn't stay back in USA itself. He wanted to return back to India to serve for the mother nation. We all are really proud of you, Dr. Badri sir. Of course, he has worked after returning from USA. He has worked for the various prestigious institutions like TAPI as well as Great Lakes. At present, he is holding the post as Head Center for Excellence in Rajalakshmi School, which is one of the premier I was telling earlier. I'm really happy, sir. First of all, I wanted to thank you, sir, for accepting our invitation. Really, I'm proud to have you for this session. But then, of course, I welcome our beloved participant. I'm really overwhelmed to see the performance of yesterday's assignment, what you have done and what you have submitted in the Google Classroom. We will share the statistics at the end of this 8th session. Really, all have done their job wonderfully. This is the word told by Dr. Prasanna Madam, who was the speaker on yesterday's class. Really, I'm happy that you all have learned Minitab and the same kind of, again, one more learning experience is awaiting for you from the hands of Dr. Badri sir. And after the end of this session, I'll appear back to answer your queries. Thanks for the opportunity. I request Vidya to further proceed.
Thank you, sir. Now it's time to introduce our eminent speaker. It's really a great pleasure in introducing our eminent speaker, Dr. Badri Toppur, Associate Professor, Head Center of Excellence, Rajalakshmi School of Business, Chennai. Dr. Badri did his BA Mathematics from St. Stephen's College, Delhi. He did his MSc Mathematics from IIT Mumbai his MS in Mathematical Sciences from Clemson University, South Carolina, USA. He did his doctorate in Industrial Engineering and Operations Research from University of Massachusetts, Amherst, USA. And he's also did his Executive MBA in Global Energy Management, jointly offered by Great Lakes Institute of Management, Chennai, and Boyer College, University of Houston, USA. His professional experience, he has a total teaching and research experience of over 30 years to date. He started his career as a teaching assistant in Clemson University, South Carolina, USA. He then worked as a teaching assistant at University of Massachusetts, Amherst. He worked as an assistant professor in TA Fire Management, Manipal, and he worked as an associate professor in Great Lakes Institute of Management in Chennai and Gorgon. Currently, he is an associate professor in Rajalakshmi School of Business, Chennai. Dr. Badri has attended over 31 national and international conferences. Some of his publications, he's published over 14 research papers in journals, 31 papers in conference proceedings, and 2 adaptations in editorship. He received excellence in teaching from Rajalakshmi School of Business. He's been invited as a speaker in many national and international conferences. His strengths, connectedness, harmony, relator and consistency, and restorative. He's visited the United States of America and Rome. So on behalf of Dr. MGR Educational and Research Institute, we really thank him for gracing us with his presence and wish him good luck for his future endeavors. So may I call upon Dr. Badri to take over the session, please. Over to you, sir.
Yes. Good morning, everyone. I hope I'm audible.
Yes,
yes?
you are. Yes.
Yeah. Okay. At the outset, I wish to thank the patrons of MGR Educational and Research Institute for giving me this opportunity to interact with the research scholars from all over India. I would also like to thank Dr. Manivandan, Dean of the new MGR campus, for coordinating all the arrangements and for making this video program happen. It is an honor for me to return this time virtually to interact with all of the students and participants. The media news is mainly about the COVID-19 statistics and what the government is doing to reduce the epidemic and what is the medical response and the emergency response. So every sector has been affected by this epidemic, and every day we get new numbers from every channel and every newspaper, and you must all be wondering how to make sense of it, how to deal with these numbers, and when would it be safe to return to business as usual, as people say. So in working in mathematical modeling, my previous experience has been with supply chain mathematical modeling, and I work in business analytics last 5 years. And so we deal with numbers, but this is the first time we are dealing with these, this disease-related numbers. So it's a new experience, and I would like to share my discussions with my friends from in Delhi, in Washington, in many places. They have all been calling me and writing to me and sharing their data and their papers. And this has created some interest in mathematical modeling of the epidemic. And I have been given some links by more experienced professors, and so I can share that. And I think you can also do that sort of modeling, as this is a training program. So one question that is uppermost on everybody's mind is, when will this epidemic flatten or reach the peak, and then it will go down, and that is the day when we can relax and breathe a sigh of relief. But now this calculation is quite difficult because this is a new virus. It's not an influenza virus, and there is people have in the Far East, they have experienced the SARS virus in Vietnam, Taiwan, China. So there is a lot of experience with this type of virus, for example, the influenza virus and the SARS virus. But the coronavirus is apparently very new, and so we cannot apply the same model exactly to this particular virus. But I thought I would show you what is there, the simplest of the existing models, and you can get an idea of how the scientists are approaching the problem. Okay, with that introduction, I think I will ask Mr. Ganesh to start the PowerPoint. Okay, so the topic for today is a case study on epidemic modeling using ordinary differential equations using Mathematica software. Yesterday, I believe you have got some exposure to Minitab software, which is a very powerful tool. Today, I will show you this Mathematica software. Mathematica is an algebraic system. It does algebra very well, and it's been there for many years, and it's got all sorts of functionality built in over the many years. And there are some demonstrations for this ordinary differential equations, and I think I'll show you that at the end of the session, around 10:45 or 11 o'clock. I'll show you that Mathematica software. Now ODEs. Now what are ODEs? ODEs are come from calculus. Many of you must have studied calculus in 11th standard and 12th standard, and also in college, those of you who studied engineering. Now, calculus is the study of functions and how the function changes over time. So usually in engineering, we talk about speed, velocity, acceleration, rotations per minute, with all those rates that have to do with engineering science. Now, when there's a function, when there's a rate of change, this derivative is required. So dy by dx, everyone knows, is the rate of change of a function y with respect to x. Now, what people have done what epidemiologists have done is apply that kind of idea to the populations. How is the number of infected people, how is it changing from day to day? Or how is the recovered population, how is that rate changing? And the immune population, that is, those who are still healthy, are they remaining healthy, and at what rate are they getting into these other compartments? So this study has three elements. One is the epidemic modeling, which requires some expertise, and I'll be sharing the basics of it because I'm not an epidemiologist. So what little I have learned about epidemiology, I'll share. And then ordinary differential equations is also very complex field. And again, I will show you absolute basics of it and what you can do with this Mathematica. And okay, so about this cover slide, I put a number of pictures on it. And this is to motivate the research discussion. You may all be aware that some people are recommending that the hygiene was to blame, that this epidemic began in Wuhan in China, and initially it was blamed on some hygiene factors in the wet market there. So the people recommended a lot of washing of hands, and we are still washing our hands many times a day. And there's those hand washes, antiseptic hand washes, and others. So is that a cause? So that's a research issue. Then WHO, which is an authority in this field, reportedly said it could be an airborne disease, not just through droplets of people sneezing or coughing. So sneezing and coughing were considered the main danger, being near somebody sneezing and coughing, and so we all wear masks. But if it's an airborne disease, then even the mask is not going to prevent the carriage of the disease. So that's another question. Is it an airborne disease or not? Then there are some videos going around about, there's one man who's saying that the 5G satellites around the world have created an environment which is very unhealthy. So the electromagnetic radiation from the 5G spectrum is causing a lot of health problems. And he says, even in the 1918 epidemic, the Spanish flu epidemic in 1918, it was just after the introduction of radio. And then he talks about World War II and the introduction of satellites in the Van Allen belt. So he's got a strong theory that the radiation is causing the poor health and epidemic. So that's another person and another school of research. Then there's those who are talking about comorbidities and old age. So there are age groups and risk groups. So in social science, I'm sure you're familiar with age groups. So you can see 9 to 12, 12 to 19, 19 to 30, 30 to 45, 45 to 65, 65 and above. So these are age groups. And are some age groups more vulnerable? It's true that diabetes and hypertension and cardiovascular diseases, they come with age. Does this apply to this COVID too? So that's another question. So old age, comorbidities are other health problems that people may have. Okay, so with this introduction, we can move on. The next slide, please. Okay, thank you. So according to my learned professor who's based in Paris, Mr. Professor Nelson McEulin, who's originally from Brazil, Rio de Janeiro University in Brazil. this pandemic began in November. So as early as November 2019, there have been reported cases, and many countries have been very slow to respond to it for various reasons. I think the main reason is we have never seen it before, and so the response is not trained. There's no trained response to it. So it's already July, so you can imagine there's 8 months it has been spreading. Now there are various databases that you can look at. In USA, the Johns Hopkins University maintains a database at https coronavirus.jhu.edu. You can note down this URL, and when you have some time, you can anyone can go. It's not a restricted database; it's public domain, and they are keeping track of all the statistics worldwide, and for each state in USA. If you have a family or friends in US who are working there or living there, you can you must be worrying about them. You can take a look. The state by state statistics. You can drill down to each district. It's very well structured. In India, the Department of Health and Family Welfare maintains a database, and the URL is https www.mohfw.gov.in. So you have statistics for India, the 35 states and union territories. So the latest figures for India were, this is already 1 week old. So this is an week-old data. The number of active cases, you can see 3,11,565, and cured or discharged with minor symptoms is 5,71,459, and deaths you can see 23,727. Now, for 35 states and union territories, the data is there. So I took the figures for Tamil Nadu. Yeah, I took the data for Tamil Nadu for 2 weeks, and you can see July 15th, we have 48,199 active cases, and out of these, 92,567 are cured, and there have been 2,032 deaths, and we have total confirmed cases. So this is how the ministry has been keeping track of the casualties and the infection. There's a reconciliation committee. The numbers were not tallying, so now there's a reconciliation committee that goes over all the records, all the the civic corporation records and the hospital records, and they are classifying the numbers again, the deaths again, and the discharged cases. So this is all quite complicated. You cannot, do these data collection, as we call it in research, is very difficult here. So we have to deal with secondary data. And I'm giving you, these are the links for the secondary data. because I don't think we have the access to the collect primary data. So these are genuine links you can get the data from. Now, some researchers calculate the doubling time. You may have seen in the papers, the newspapers, some researchers talk about the doubling time of the infection. So how many days does it take for the infection to double? Now, if that doubling time increases, that means the epidemic is slowing down. If the doubling time decreases, then it's danger. So that's some people do that sort of research. Then this last bullet point, um, I on LinkedIn, which is a networking site for professionals, people looking for jobs and professional networking. I made contact with a OR professor, a senior OR professor from Columbia in South Carolina, in South America, excuse me, and he introduced me to the ODE models, ordinary differential equation models, epidemic modeling. So it seems for 100 years or 90 years, people have been applying this ODE models. Now, I have not touched ODE or ordinary differential equations since my IIT days. I've been doing other sorts of work. So suddenly, here was this professor who was saying you can use differential equations to model this data. So I remember the famous Professor Pani in IIT Bombay. There's one Professor Pani who taught this course. So I was trying to remember him and what he had taught. Next slide, please. Yes, thank you. So here is a website in Oxford, United Kingdom. So Oxford is developing a vaccine, and everybody is very hopeful about the Oxford vaccine. India also, there's on Bharat Biotech, which is coming up with a vaccine. Now, vaccine takes years to develop, but this is the first time that these pharma companies have been working day and night to go through all the protocols. So it's very lot of protocols to go through before you can market a vaccine. So Oxford is one famous institution. So they have this Our World in Data, OWID, for Our World in Data. And they keep data, they are maintaining data on 207 countries and all sorts of data, demographic data, socio-economic indicators. And since this epidemic started in November, they have been maintaining data from December 30th onwards. And you can go to this link, ourworldindata.org, and download the Excel file or CSV file. If you use R programming, you can use the CSV file. If you know Excel, you can download the Excel file. So here is what I found in the data set. My friend, I have one friend from St. Stephen's who's working in the World Bank in Washington, DC. So he called me about 2-3 weeks ago and said, there's this data set, and I would like you to take a look at it. And I'm writing a paper on which countries have dealt well with the epidemic and which countries have not dealt with the epidemic, and what could be the reason for that. So I got this data set and looked at it, and it's got 27,600 observations for 34 variables. So it is big data. Excuse me. I got a call. Yeah. So look at the data set. I'll just run through all the variables quickly before we get to some analysis. So the first is ISO code. This is just a standardization code, and it can be used when you are filtering data. Suppose you want to filter data. This is too many countries, 207 countries. You cannot analyze at the same time. So you may want to look at 16 countries or 3 countries or just one. You may just want to look at the Indian data. So you can filter the data using the ISO code. So that's what it's useful for. Then we have continent. So continent is, there are 6 continents in this data set. And one interesting thing I noticed was Central America. Central America is, Panama, Mexico, Costa Rica, those countries that come between North America and South America. They have been categorized with North America. So we have North America, South America, Asia, Europe, Africa, and Oceania. So they have just used 6 continents. And of course, you may want more continents in the classification. That's entirely up to you. Location. So there are 207 countries, as I mentioned. Then next date. Date is from January 30th onwards. Every day they update the numbers. Then here come the epidemic cases. Total cases. This is a count. New cases. Every day, how many new cases are reported. And so this is a cumulative. This is a daily count. This is cumulative deaths since December 30th or December 31st. This is new deaths every day. So we hear about this count at the national level and the state level. Then next row, the next row is total cases per million. So they form these ratios. So this is called data transformation. So if you form some ratios from the given data, that's called data manipulation or data transformation. So you may want to form these ratios, that is total cases per million, new cases per million, total deaths per million, new deaths per million, total tests. Now, total tests is a very important variable. How many tests are being performed every day since the start of the epidemic? This is new tests is everyday data. Total tests is cumulative number of tests. Now, testing is how we get all the numbers. You cannot get any idea of the epidemic unless you test. So Indians, Chennai has set a record of 5 lakh tests recently. And so every city is testing. Mumbai has been testing. They have had quite a hit. So they have been testing. Delhi has been Delhi, the reports are good. The curve has gone down. So this is all based on the tests only. Otherwise, you cannot tell. Then these two are total tests per 1,000 and new tests per 1,000. Then third row, we have new tests smoothed. Now, smoothed means it's an average of the last 7 days. So you take a moving average of the last 7 days data, that's called smoothed. So this is new tests smoothed per 1,000. Now, tests units. Now, this is what is their sampling procedure? Are they doing systematic sampling or cluster sampling? So it has to be random sampling. For statistics to work, it has to be random sampling. I think you all know that. But what's happening in this situation is there's a lot of that tracing is there through the apps. So many people are being traced, through contact, or initially that was how it happened. So when the passengers were flying in from abroad and were found COVID positive, their contacts were traced and they were also tested. So in the initial stages, the testing was not random. So you really cannot apply statistics to those that data. But now we are 6 months into this. The sampling is more random. So I think you could apply the statistics. Now, next is, these are policy variables, stringency index. So this is the one I want to talk to you about today. What is stringency index? Stringency index is from 0 to 100, a number on the scale from 0 to 100. And it is a measure of how tough the government policy has been. The travel ban or the lockdown of the closure of schools and public malls and all those places where people gather in large numbers. So this School of Public Policy in Oxford has come up with the stringency index. So I'm going to tell you about that, what I gathered about it. Then here are usual demographic variables: population density, median age, what fraction of the population is 65 years old or older, and what fraction of the population is 70 years old or older. So this information is used in many studies. Then GDP per capita. So GDP is a economic variable, gross domestic product. So this ratio is per capita GDP. Now all the industries are hit, so the GDP would have really gone down, but we are using historical data. This is not current data. This is 2017 data or 2010 data. So some of this data is historic. Then they have a poverty index, they have CVD death rate, the diabetes, then female smokers, male smokers, hand washing facilities. So this is related to that hygiene factor. Then hospital beds per 1,000. Hospital beds again is one. It's been in the news. Bangalore has had a spike day before yesterday, and people were not getting hospital beds because they had not taken the test. If you have not taken the test, you are apparently not allowed. So one question is, what does the smoothed mean? So new tests smoothed and new tests per thousand. These are just ratios like the previous ones, new tests per thousand and new tests per thousand. I think there's a repeat here. This total tests per thousand and new tests per thousand. So what is the difference here? This is smoothed means it's a moving average. So smoothed means, let me write this. Smoothed. Okay. Smoothed means so smoothed means it's a moving average. So smoothed means moving average of the data. So you could take a 3-day moving average or 7-day moving average. So it's means you are not following every peak, every spike, and every drop. So you're trying to find some some trend line by smoothing the data. So instead of taking a regression, you can do this moving average. Okay, then finally, life expectancy. Life expectancy has been noted for many years, and every country has been raising the life expectancy. So that information is also there. So next slide, please, Mr. Ganesh. So I've been telling you about, I'll go quickly through these next few slides because I've already told you what they represent. So I'll concentrate on this third column. Now, where do we where have they got this data from? So ISO is from International Organization for Standardization. Now, these three variables are from our world in data. The epidemic data is from European Center for Disease Prevention and Control. So there's one ECDC. There's a center called ECDC, and they are noting these epidemic statistics from every country. Next slide, please. Yeah, so you can see most of the data is from ECDC, and the testing data is from national government reports. So the government has to provide, each government has to provide the report on the total testing done. So total tests a day, total tests over the 6 months or 7 months, and then new tests, and all these related facts have to be from the government reports. Now, India started only from March 30 or thereabouts. So, two months there was a delay, and that some countries they have started slowly off the block, and So, but they have caught up, and they are as good as any other country now in terms of reporting. Okay, next slide, please. Okay, so here, this is the stringency index that I was talking to you about. This is a composite measure based upon 9 response indicators, including school closures, workplace closures, and travel bans, rescaled to a value from 0 to 100. So 100 is strictest response, and 0 is most lax response. And this is maintained by Blavatnik School of Government. So this is a School of Public Policy from Oxford. Then population data comes from United Nations. Population data comes from World Bank, World Development Indicators. Okay. So this is UN data and World Bank data. Now, next slide, please. So these are the age group and risk group. So the age group data, this comes from UN Population Division, World Population Prospects, excuse me, 2017. So this population data is 2017. And the age group 65 or older, 70 or older. These are also World Bank, World Development Indicators, also from 2017. Then one data source is UN Department of Economic and Social Affairs, 2017 revision. So you have to give your source. You have to acknowledge the source of your data, and so that's very important, because everybody is, not in the same country, and this is a worldwide epidemic. So you have to reconcile the data sometimes, and 1 year data maybe from some data maybe from 2017, something maybe from 2010. So you have to be clear about all this in your study. Then GDP per capita. So GDP is per capita is from World Bank. Extreme poverty. Share of the population living in extreme poverty. Excuse me. Most recent year available since 2010. Then cardiovascular disease is CVD, death rate, and there's a global burden of disease collaborative network, which is the source for this CVD data. Next slide, please. Okay, here are the last few of the variables. Diabetes prevalence. Now, diabetes is, many Indians have this problem. So this is a comorbidity. So percentage of population from age 20 to 79. What percentage have diabetes? Then female smokers, male smokers. So smoking, they've got some data. Then hand washing facility. What share of the population has a hand washing facility on premises? So the United Nations Statistics Division. Then finally, hospital beds per thousand. So how many staffed beds? So in some people say staffed beds, that is how many of these hospital beds are available per thousand citizens. So this data is from OECD, a couple of sources, Eurostat, World Bank, National Government Records, and other sources. Then finally, life expectancy at birth in 2019. James C. Riley is the source, Clio Infra UN Population Division. So these are all the variables in the data set. Now, where did I find this? It took me some time to locate the code book, which is available at GitHub. Now, you may all know about GitHub. It's a repository for all the software and questions and Q&A for computer languages. So GitHub is, you can find this information at GitHub. I've given the link below. Okay, let's move on to the next slide, please. Okay, so now if you filter out the data for India, it's about 200 rows. So out of 27,600 rows, only about 200 rows are the data for India. All the rest are for the other 206 countries. But we are very concerned with those 200 rows. And the population given is this big figure, 1,380,004,385, 138 crores. So if you're doing research, you have to decide what hypothesis you are forming. Then you have to select the variables and decide what type of test is appropriate. And for that, you must first look at the data types. So some data is character data, like the country name. Some data is integer. So all the counts are integer. Then all the indexes and all the ratios are real numbers. And I noticed there are no logical variables. So in statistics, you use a lot of indicator variables. Now, there were no logical variables or indicator variables in this data set. So I thought I would show you how we can make a indicator variable and what use we can make of it. So we can make a pivot table after forming a indicator variable. So I took the stringency index. Now the stringency index we learned is between 0 and 100. So I was thinking, suppose we say that a stringency index below 50 is not stringent, and 50 and above is a stringent government or public policy. Then we can have a 0-1 variable. Similarly, take GDP per capita. GDP per capita could be any number. So we can normalize it. We can divide every number by the maximum GDP. And that way we can scale it from 0 to 1. So that's what I'm going to show you in the next slide. So now I took 30 countries out of the 207. If you go from A, B, C, if you take all the countries starting with the letter A, B, C, you start from Afghanistan and end up with Cameroon. So from Afghanistan to Cameroon, there are about 30 countries, and they are in no other order. So there is no, it's alphabetical order, so it's quite random. So I've taken 30 countries that way. Now you may want to pick your countries in a different, using a different criterion. That depends on your research. So I didn't do that. I just took the first 30 countries, and we are going to categorize them as stringent and non-stringent. And then we can cross-tabulate them across the 6 continents. So remember, there are 6 continents. So there's stringent, non-stringent, and then how many fall in each class of the 6 continents. So I thought we could try that out. So since the observations are given for 6 months, for each country, we have to average out 6 months data. So we don't have one row for each country. We actually have 200 rows for each country. So if you want one number, you have to average out the stringency index or GDP per capita. Okay, so let's move on to the next slide. So here you can see the countries I've taken. Afghanistan onwards to Canada. So after Cameroon, there's Canada, maybe 1 or 2 more. So I took, excuse me, I took these countries. The continent is given, those 6 continents. Now this is the stringency index. You can see Afghanistan is 67.59. Albania is 84.26. Algeria is 65.28. Andorra is 50. So every country we have the index from 0 to 100. And some are low numbers. You can see Belarus is 8.33. Burundi in Africa is 22.22. So some indices are high and some are low. So I've taken I formed an indicator variable here. The rightmost column is, if it's above 50, we give it a score of 1. If it is below 50, we give a value of 0. So Australia, which is a developed country, you can see the stringency index is 35.65. Austria, which is also a developed country, is 43.52. The score is 0. Then a couple of countries here: Burundi, Cambodia. Cambodia is low stringency index. Now Vietnam is not in the list because the V comes right to the end. But Vietnam is a success story in handling epidemics because they have had previous experience with the SARS virus. In 2003, there was a SARS epidemic, if you all remember. So countries which have dealt with SARS, they moved fast when this epidemic struck, and they took adequate measures. So some countries have low stringency index, but they may have done well as a health record. So this is not, it's a little complex. So I thought we would discuss this for some time. Next slide, please. So here's a histogram. you can see the class intervals of the stringency index, 8.33 to 18.33, then 18 to 28, 20. So these are class intervals of 10%. And you can see there's one country in the first stringency index class, then there are two, then this class has 4 countries, and this 58% to 78%, there are 6 countries. So there are 18 countries here in this the middle range, and there are 3 countries with very high index. Okay, so let's move on. Next slide. So this is this is the indicator variable. So this is if you round off to 0 or 1, you can see 5 countries are 0 or no stringency, and 25 are high stringency. So it appears most countries are quite stringent. I'll explain what that means again. Next slide, please. Now this is the same data, but this is the same data, but we are, the continents are there, the 6 continents. So you can see which continent has what stringency index. Okay, so you can see South America has this gray and blue colors, which means it's the most strict. So South America, Bolivia, and some other countries have the highest strictness. Now, Brazil, has been impacted very badly. So there are some exceptions. The Brazilian government has not been very strict. They have allowed a lot of economic activities. So this is not representative of South America. So I think you have to take all countries to really decide this sort of thing. Now, Oceania is over here. It's in the gray area. North America, Africa. Africa, you can see all the colors are there, but the gray is not there, which means it doesn't have super high stringency. Now, Asia, the dark blue is there. Europe, you can see the gray is there, which means high stringency. So next slide, please. I'll try to wrap up the presentation. So this is the binary scale. So this is how many continents are in the low stringency or no stringency, and how many of the continents feature in the high stringency. Next. So next slide. So this is some plots from R. So I imported the data into R, and this is using ggplot. So there's a package called ggplot2 in R, and you can get plot this big data sets. Next, please. Next slide. So this is new tests. How many tests are made every day? This is United Kingdom, new cases, and new deaths. You can see it's quite flat for 2 months. Then there's a sudden spike, and then the new deaths, the daily deaths drop. And here also the new cases is on the decline. So they have managed the epidemic well. Next slide, please. So this is USA. Again, you can see there's no problem for about 2 months, and then there's a sudden spike, and they have not done very well. You can see the cases has gone up, but if you look at the new deaths, they have controlled the illness, so the casualties are low, although the spread is quite high. Okay, next slide, please. Now, India, I've already shown you the data. So you can see the curve is quite low. It's not, the deaths is under 500. So the Indian doctors have done a very good job. Okay, next slide, please. So coming to this Mathematica model, I'll just, I thought I'd show you. So these are the compartment models. So you create compartments about how many are susceptible population, and one compartment is the number of infected people, and R is for recovered population. Voice is not audible. So
sir, voice is completely audible, sir. You
okay.
Yes, yes.
Yeah, voice is audible. Okay. So these are the three variables, and we form the differential equations. And beta and alpha are parameters, number of infections per unit per time. So beta is an estimate of how many people does one infected person spread the infection to. And alpha is recoveries per unit time. So I've shared this paper with Dr. Manivandan. If you are interested, you can ask him to share it with you after the session. So next slide. So this model is for influenza. Influenza is not to be confused with coronavirus. So it's a different virus, but this model, you could see how they work on it and get some idea. So let's take beta equal to 0.06. Now, what could this mean? This could mean that if one infected person meets 100 people, 100 normal uninfected people during the day, then 6 of them would get infected. So if there was no lockdown and you went to school or office, or you went to Express Avenue or went to the mall, then you may infect 6 people during your day. Now this beta has to be estimated. I've taken 6% from some data, but I'm not 100% sure. It may be more, maybe less. Then there's another important variable, which is called alpha, which is the duration. 1 over alpha is the duration of the epidemic or the infection. So alpha is the recovery rate. So mathematicians can see if there's a negative sign, it means the slope is negative. So the rate is negative here. The infection rate goes up and then it goes down. So we are trying to find where the peak is, and the recovery rate is positive. So it's upward, it's increasing. Now, if you set I prime t equal to 0, then you can get the turning point. And so you can get the turning point to be at alpha divided by beta. So if you find the turning point for I prime of t, you get alpha by beta. So once you get alpha and beta, you can find out when the peak will, when the epidemic will reach the maximum and start going down. But the problem is this alpha and beta is not easy to calculate. And so everybody has different guess when it will peak. Okay, so let's move on to the next slide. So the pioneers I've mentioned here, Kermack and McKendrick, who have done the earliest of these models. So basically, this is the same concept. The basic reproduction number, that's the one parameter that's calculated. If it's greater than 1, it is an epidemic. If that R0 is less than 1, it means the epidemic reduced. So basically, the controls are to bring the R0 to less than 1. And I've told you earlier, the R0 is related to the beta and gamma here. Okay, so let me show you the next graph. So next slide. So suppose we are trying to find the recovery rate and the infection rate. Now, according to my friend who's keeping track of the numbers, the recovery rate is 63%. So every day, quite a few numbers are discharged as recovered. So if you take it as a percentage, it's 0.63. And the infection rate is about 7.5%. From the number tested, about 7.5% are declared positive. So if you form this ratio, beta by gamma alpha, you get about 12%. So from this sort of calculation, one would conclude that about 12% of the population would get infected before the epidemic declines. Now, this is just a number, top of my hat. It's has to be verified by the medical community. So I'm just showing you how these calculations work. I'm not guaranteeing these numbers are very correct. Okay, next slide, please. Okay, so this is the demonstration, Mathematica demonstration. Mr. Ganesh, if I can use my if I can be the presenter.
Now you can be presented.
Okay, so can you see this? Okay, I think I have to say share, right?
Yes, sir.
Yeah. So tell me if you can see this graph. I'm showing a epidemic dynamics graph.
So it's loading, sir.
Okay.